Okay, so we've been looking at the relationship between rectangular coordinates and equations and polar coordinates and equations. Now we want to bring in the calculus. And we want to start looking at derivatives when we've been given something that's been defined for us, a curve that's been defined with r's and thetas instead of x's and y's. In other words, using polar coordinate system instead of rectangular. So here I have an example. I have r equals 4 sine theta. Now remember, if we're trying to decide what this looks like, one of the things you can do is you can convert it. So I could do this. I could multiply both sides by r and take note of this. Over here I have r squared, and over here I have 4r sine theta. Now remember, we have a couple of things that we can keep in mind. We have that x squared plus y squared equals r squared. We know that. And we also know that r sine theta is equal to y, and just like r cosine theta is equal to x. With that in mind, look what we have here. We have that x squared plus y squared, that's this, is equal to 4y. Now looking at that, you can tell that what the shape that's involved here is a circle. And to make it even more clear, I can bring the 4y over. Whoops. Can bring the 4y over and complete the square, and I'll have even more information about what where this circle is located. So if I complete the square, if I take half the 4, square it, and add it, I get this. I get x squared plus y minus 2 squared equals 4. I took half the 4, squared it, and added it to both sides. And now you can see what we have here is a circle that's centered at 0, 2, and has a radius of 2. So immediately you can tell what the circle looks like. Well, maybe we don't want to have to go through all that work every time. Maybe we would like to just recognize some basic shapes, like what r equals some constant times sine. What does that look like? Well, we can plot a few points here. Let's just plot some values for theta, and we will look at the corresponding values for r in this one. Now we start off, if I put in a 0 for theta, sine of 0 is 0. So if I were going to plot over here, I'll just get a 0 right here. So when the angle is 0, r is 0. Now what I have here is I have this polar grid, and in red I've highlighted, I have 0, 30, 60, 90, and I've just went around that way. In other words, I've skipped these middle, these 15-degree ones, like this one 15, and so forth. So I'm just going to plot along the red. Now the next thing I come to is the pi over 6. Well, sine of pi over 6 is 1/2. 4 times 1/2 is 2. Okay? So I'm going to do this. Let me do this. So I'm going to count these as a half. So here's 1/2, here's 1, here's 1.5, here's 2. Right there. So I get that point. Okay. Now let me do a pi over 3. Sine of pi over 3 is the square root of 3 over 2. And if I multiply that by 4, I get 2 square roots of 3. So I get 2 square roots of 3. Now we want to plot that, and that's about 3.4. So let's see here. Here's 1/2, here's 1, here's 1.5, here's 2, here is 2.5, there's 3. So I guess it's about right there. You know, something like that. Now, if I go to the next step and do pi over 2, sine of pi over 2 is 1. 4 times 1 is 4. So here we go. We've got 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. So I guess it's up here like this. So it looks like if I want to do a sketch of this, you know, it's going to be something like this on this side. And we could keep on playing this game, but this is enough to show you how these things are plotted. Now, I'm going to go ahead and look at the graph of this with my calculator. You want to make sure you're in polar mode, and I'm going to go 4 sine theta. Okay, delete that extra theta in there. I go to my window, and I'm going to set my window from 0 to pi. And now that's not really my window, that's the value for theta. My window, I'll go from -5 to 5 on the x and the y. And then we can look at the graph. And there it is. Now it looks like this function does everything it's going to do between 0 and pi. Now I could have it graph more. For example, I could change this window, and I could go or change my values for theta. Instead of going from 0 to pi, I could have from 0 to 10 pi. And now you can see the animation, the thing just keeps going around. So it's enough to set it from 0 to pi. We don't need to go through 0 to 2 pi would just be redundant. It would be 2 times around. Okay, now what I want to do though is I want to talk about the derivative, finding the derivative of this thing. R equals 4 sine theta. And in particular, I want to find dy dx. Now you notice this R and theta, they don't have y, there's no y or x there, but I want to find dy dx. Now let's see how we could go about doing that. Remember, we've talked before that we've noticed this relationship that x is equal to r cosine theta, and y is equal to r sine theta. We've taken note of this before. Now something else that we've taken note of before is this. We said that if you ever have a function, and let's suppose you have a parametrically defined function here, or an expression. Let's suppose you have x equals f of t, and let's suppose y equals g of t. We've taken note of this before, that if you want to find dy dt, then you're going to take g prime of t over f prime of t. In other words, the derivative of the y over the derivative of the x. Oh, and this is dy dx. Sorry about that. Dy dx would equal that. So this is what we've taken note of before. Now, we've got this relationship. And we've also, for our particular problem, we've got r is equal to 4 sine theta. That's what we have. We've been given that. In other words, we've been given what r equals. R equals this. So let me use what I've learned about finding dy dx with parametrically defined curves and see if I can use it here. So I've got x equals r, well, r is 4 sine theta. Okay. And y is equal to r, which, well, that's 4 sine theta. So we've got x and y. Now I can use, I can find the derivative like I've learned before with parametric curves defined parametrically. But before I do that, let me see if I can make this a little simpler. Since we're going to have to do some calculus, maybe I could write this as 2 sine 2 theta. That seems reasonable because this right here is 2 times 2 sine theta cosine theta, and this is sine 2 theta. Now I can do something similar down here. I recognize that this is just 4 sine squared theta. Okay, now once I have that, once I've established that, I can come back and I can say, oh, okay, let's find dy dx. Okay, dy dx, I'm going to take the derivative of this y. So that's going to be 8 sine theta cosine theta. Just use the chain rule there. Now down on the bottom, I'm going to take the derivative of with respect to theta, and I get 4 cosine 2 theta. 4 cosine 2 theta. Okay. Now let me just simplify this a little bit. Notice that I could write this as 4 times 2 sine theta cosine theta. And down here I've got 4 cosine 2 theta. And these 4's will cancel, and up top I get sine 2 theta over cosine 2 theta. Okay, so that is dy dx. This will give me the slope of the tangent, the change in y with respect to x. That's what that will give us. So let's see this in action. Let's suppose that we want the slope of the tangent at pi over 6, for example. Okay, so let me put in the pi over 6. So I'm going to take the sine of 2 theta, so this would be 2 times pi over 6 over cosine 2 times pi over 6. And I get sine of pi over 3 over cosine pi over 3. And this is equal to the square root of 3 over 2. And down here we get 1/2. And that's just equal to the square root of 3. So that's the slope of the tangent whenever theta is pi over 6.